Okay, welcome to Lecture 10. Again, I'm going to split this up in halves. Overall, I don't think this is a terribly long lesson, but I'm still going to split it in half. Okay, so in new color scheme, I'm going to go white with predominantly black drawing, writing, and I'll just kind of ask you guys if you prefer this over the other, black with white, drawing. Anyway, so today we're going to be talking about acceleration and control volume. With this lesson and then into the next one, it's a little bit esoteric, a little bit kind of like, well, okay, when am I going to need this in this class? But we're going to start to, as we get into the control volume, we're going to start to get back into things that are really, really valuable. So, so I'm going to start with acceleration, and acceleration is really important. It's just that for you guys, most of the time, this is not really going to show up all that much. I'll call this the A total, okay? And this is going to the acceleration total, and this is going to be along a streamline, okay? And so the acceleration total, now you might typically think, well, okay, well, that's the change in velocity with respect to time, okay? dv dt, okay? But then, and that kind of works, but we need to account for the fact that something can be accelerating as it moves in the streamwise direction. So that looks like this, ds, where s is the direction along the streamline. So for example, if I have a particle and it's, a fluid parcel, and it's flowing along this streamline, okay, at various times, okay, you could imagine that this thing, so this is like the Eulerian versus Lagrangian difference. So that particle can speed up for one of two reasons. So one, this is for what we call the local acceleration. So this is basically because the flow field is speeding up. So like at this location, the difference in the speed between time 1 and time 2 exists. Okay, so for whatever reason, the forcing is changing or whatever. So something is, so it accelerates because of that. But then the flip side is this one right here, which is what we call the convective acceleration. Okay, and this is due to the fact that there's a difference in the velocity here versus here. So as the fluid moves between those two locations, even if nothing is changing in time, it accelerates. So this might happen in a nozzle, so you might have a streamline that's going like this. Okay, and so it might be moving fairly slowly out here, and then as it goes over here, it speeds up. Okay, and the reason for that is convective acceleration. Okay, even though nothing's changing in time, this fluid parcel is speeding up as it goes from point 1 to point 2. Okay, you could also think of this as like flow over a waterfall, right? So you've got kind of a river, and there's a little thing like this, and the water's going over this waterfall. And nothing's really changing in time, but if you're a little parcel of fluid, as you get close to that, you start to accelerate. Okay, that's convective acceleration. Okay, the local acceleration would be right here, and that would only be happening if things were changing in time. So for example, if, I don't know, it was raining, and so this water surface were increasing. So because the water surface were increasing, the velocities of all the fluid particles in this system were increasing. Okay, d by dt. Okay, so this is along a streamline. However, more typical the way we do this is we do this in Cartesian coordinates. And I'm going to write all this out, and then I'm going to, while it's paused, and then you're probably going to want to pause it and copy it. Because when I'm in class, you usually have to just stand there for a few seconds while everybody copies all this. So just bear with me. All right, so in Cartesian coordinates, the local acceleration, so you might spend a couple seconds and copy all this down. So anyway, so the acceleration in the x direction, and if we kind of look at this and compare it to up here, hopefully you'll see kind of where this thing is coming in. But first of all, this is the local. Okay, the first term in each one of these is the local, and the next three is the convective. Okay, acceleration. And so what we're seeing here is the acceleration in the x direction has to do with so this is the change in the x direction velocity. So u is the x direction velocity, v is the y direction velocity, and w is the z direction velocity. And so what we see with the locals, we see du dt. Okay, so that's how things are changing in time. Okay, And then what we see with these other terms, with these three, these convective, is basically we're seeing how the u velocity is changing. Okay, in this case, it's, so in this particular term right here, the second term, or the first, I guess the second term, but the first convective term, what's happening is this, the u velocity is carrying in fluid that either has more or less momentum in the u direction. Okay, and like right here, for example, the v velocity is carrying in u fluid that, so I'll draw a picture for you. So for example, if this is, say, just a little block of fluid, then what's happening is the fluid going in the x direction, so the u direction fluid like this, it might be different on the top than on the bottom for whatever reason. Okay, now that is being carried through the fluid by v, or through our little block by v. Okay, so what is this doing? Well, it's carrying low momentum fluid here, low momentum, low u fluid, into a block that generally has higher, or at least that on the top has higher u. So obviously somewhere in the middle, it's, between those two, right? So the net effect of this v velocity is carrying this low u into this area that has medium u. Okay, so it's slowing it down by mixing it out. Okay, so that's kind of what this term is right here, and we can do that for any of these convective terms. Okay, so basically in this case it's slowing it down. If we had an alternate case where we had higher momentum on the bottom than was on the top, and say middle in the middle, and v were in this direction, then what would happen is it would be carrying this high momentum fluid into this block, and once it got into there, it would cause it to speed up. Okay, and so that's what this is doing. Okay, and we have this in all of the directions. So you should see the patterns here. This particular, like if I look at the acceleration in the y direction, they're all derivatives of v. And then this first one is d by dt, and that's going to happen for all of these. And then for each of these others, it's u d by dx, v by dy, and w by dz. Okay, and you'll see the same things on all of these. Okay. Now, what happens a lot in fluid mechanics, or really just in a lot of other things, is they give this a special name. This is called the material derivative. So they'll call this dw, usually it's a lowercase d, sometimes a capital case d. We're going to go capital D. Okay, this is called the material derivative. This is the material derivative. Okay, and I don't know why they call it that, so I can't really help you there. I don't think it really matters. I'm never going to ask you what is the material derivative. But basically, if ever you see a capital D for a derivative, that means you need to expand it to look like this. At least if you want to do the math on it, which you may or may not want to do. Okay, so, all right, so I'm going to do an example on this problem. And we're going to just do a couple examples. So I'll pause it and, write out the example. All right, so we have a diffuser in this case. And the diffuser is kind of the opposite of a nozzle. Basically, the fluid flows in at V1, it flows out at V2. Okay, so the question we're going to ask right now is, so as the flow spreads, okay, you can imagine it's going to slow down because it's got more space. Okay, so basically V2 is going to be less than V1. Okay, so now as we're thinking about this, we want to know, is this uniform? Okay, is the flow through this diffuser uniform? So basically what I'm asking is, is the flow everywhere, let's say in the streamwise direction, is it always the same? Okay, and the answer is no, because V2 is less than V1. Basically because the cross-sectional area, the area of this, the diffuser, it changed. It went from small to large, so everything is going to slow down. So this is not uniform. So the answer is no, it's not uniform. Okay, what about steady? Is the flow in this thing steady? So in this case, I'm asking, is the flow changing in time? Not for an individual particle, but for like you who's looking at this from the side. And the answer is, well, really we don't know because I didn't give you enough information. But there's no reason to think that anything is changing in time. Oh, that's the wrong kind of V. We want a velocity. Okay, so let's make it a u dt. Or really, I guess we want, really, I guess in this case, we want the velocity, just so like a capital V to represent velocity. So dv dt equals 0. Okay, so it's not accelerating in time. The forcing is not changing. Okay, and I guess I could say over here dv dx does not equal 0 because the velocity is changing in the x direction. Okay, so how would we get the acceleration here? Well, we could do this in Cartesian coordinates if we wanted to, and we could deal with all these things, but I'm just going to use the streamline stuff. So what I'm going to say is I'm going to say acceleration. So I'm going to say acceleration in the x equals dv dt plus v dv dx. Or really s, I suppose. Yeah, we'll make it s, so along a streamline. Okay. So ds. Okay, so if we do that, then we note that dv dt is 0 because there's no acceleration. So in this case, the acceleration is only along the streamline direction. And it's only because the particle is just like along a streamline, and the streamline itself happens to be accelerating. Okay? So let's do another example. Okay, that one was non-quantitative. So in this problem, we have a nozzle, so the opposite of the diffuser I just showed you. Okay, and the flow is entering on the right, on the left, and exiting on the right. And it's entering at a velocity of u naught, or u0. And as it moves through this nozzle, somebody somewhere somehow figured out the equation for the flow velocity as a function of its position, x. And it is u naught divided by 1 minus x over 2L, where L is the length of the nozzle, okay, as drawn down here at the bottom, okay? And so what we want to know is what is the acceleration at x equals L over 2, okay? So what we do for this is, well, we're going to decide a few things. So first of all, I want to know, is it steady? Okay, and if this is the definition of the velocity, and it doesn't show any way that it's a function of time, so it wasn't given as u as a function of x and t, it was just as a function of x, so that means it's not a function of time. So we're just going to say that, yeah, it's steady. Okay, so nothing is changing in time because du dt equals 0. Okay, what about uniform? Is it uniform? Well, definitely not, okay, because u is a function of x. We've got the x right here. Okay, so therefore it is not uniform, which means that if I want to find the acceleration of this thing, and we're going to go right along this middle streamline here. So I'm going to say, okay, well, I want the acceleration in the x direction. So that's du dt plus u du dx plus v du dy plus w du dz. Okay? All right, so sorry, I had a little mishap there. Okay, so as we work through this, well, we note that in this particular nozzle, there's really no flow in the y or z direction, such that they're not even defined. So I'm not even going to worry about v or w. Okay, and then this thing goes away because it's steady. Okay, so all I have left is this one term, u du dx. Okay, so u, we note, is, so if I copy u from up here, I'm going to end up with u naught, 1 minus x on 2L, times the du by dx, so now that's going to be u naught over 1 minus x over 2L. Okay, so now this is just a math problem. Okay, so notice the only acceleration that's happening here is the convective acceleration. Okay, again, remember these are the convective acceleration terms. Okay, so ax equals, I'm just going to copy this first term, u naught for 1 minus x over 2L. And then I'm going to take this derivative. Okay, and we'll note that the u naught is a constant, so it can go out front, so we don't need to worry about that. But then I've got this 1 minus x over 2L, which I could think about as kind of like, I could think about it like this, 1 minus x over 2L to the negative 1, right? So when we take the derivative of that, we're going to get, it's going to go down a level, so it's going to be -2. So that'll means it'll be on the bottom. 1 minus x over 2L squared, because it's on the bottom, so it's a -2. And then we will need, let's see, so that means, so it also brought a negative sign. So we've got a negative out here. Okay, so it's going to be u naught times all this business. And then we need a chain rule. And the chain rule, we're taking the derivative with respect to x. So in this case, the chain rule is -1 on 2L. Okay, so, and you might be able to hear Cooper playing with my dog in the background. I will apologize for that. Okay, so we're going to do the math here. And we're going to get, a pretty ugly expression, noting that I can combine these two, 1 minus x on 2L's. Okay, so I get that to the third power. The negative signs cancel and become a positive. I've got a 2L on the bottom. And it looks like I've got u naught squared on the top. Okay, so the temptation at this point is to say, okay, we figured out what the acceleration is. Except we haven't, because the problem specifically asks, what is the acceleration at x equals L over 2? So what we're going to do is we're going to go down here and we're going to plug that in. So wherever we see x, we're going to say L over 2. So this is the acceleration as a function of x. Okay, so if I wanted to know the acceleration at any given point, I could just plug in x and I would get it. But I want to know when x equals L on 2. So I'll go ahead and plug that in. So we get u naught squared over 2L, 1 minus x on 2 divided by 2L cubed. Okay, and let's just, do the algebra here. And we're going to end up with, well, it's going to get a little bit ugly. So this term right here becomes x over 4L. Oh, wait, is that right? No, I'm sorry. Wait, what did I do here? Oh, all right, this should be L over 2. My apologies. This should be L over 2. I was wondering why the L's didn't cancel out. So I should have plugged in L over 2 here. Okay, so then L over 2 divided by 2L becomes 1 over 4. So 1 minus 1 over 4 becomes 0.75. So I end up with u naught squared over 2L times 0.75 cubed. Okay, and so ultimately this becomes acceleration of x equals L over 2 equals u naught squared on some number of L's. Okay, and if I do all the math and keep track of all the things and cube all the things, it becomes 32 on 27. Okay, so that's pretty cool. Okay, with both L and u naught being constants. Okay, so that's the solution to that sort of problem. Okay, and so that's all I got for A, and we'll go ahead and we'll go to B. So, all right, again, as always, take care of yourselves. Know that Dr. Wagner loves you, even though he doesn't know you, because he never met you guys. But take it easy. All right, bye. So,